Hi, my name is Aaron Jerome. This is a series that introduces digital electronics, beginning artificial intelligence, and leads towards designing automation. This topic is an introduction to state machines. Again, this is State Machines, Part 1, Introduction to State Diagram or State Transition Diagrams. This is a student interaction worksheet. It allows students to participate with the presentation. In this presentation, I'm going to be focusing on transition diagrams. A word to the wise, this presentation requires some prior knowledge. Specifically, you have to understand the following. Truth tables, how they can turn an idea into an equation. K-maps or Carnot maps, how they can simplify an equation. Simple circuit design, how to design a circuit using simplified equations. Flip-flops, how they synchronize and control data. Waveform analysis, plotting, reading, predicting signals over time. If you don't understand these prerequisite ideas, then you are not ready to understand state machines. Viewing this presentation might hurt your brain and discourage you. Please watch my other videos on these prerequisite topics, understand them before attempting to learn from this presentation. Could you design a machine that can drive traffic lights? A full-blown computer is not an efficient use of technology. There's just too many wasted components. What we need is the minimal machine that can be self-driven and do the job. I believe these are Swedish traffic lights. Notice they have 4 states here, and they have one state that has both a red and a yellow light showing at the same time. The image below the traffic lights is a very simplified state transition diagram. Sometimes it's also called a state diagram, a state graph, or a bubble graph. This is a diagram graph that was used to plan out how a garage door works. The circles are called states. At some time, each one will be the current state. So you could be in any of those states: door up, door stopped, going up, door opening, door down, door stopped, going down, and door closing. The arrows between the circles are called transitions. The notations on the arrows are if-then statements. Sometimes they are called input-output statements, if-then statements. They may also serve as a report to the observer. State graphs are not circuits of wires and components. And some students mistakenly believe that this is a wiring diagram. It's not. They are instead a sketch of an idea from a mind, usually to a paper or at least an electronic device. These I just circled the little if-then or input-output report statements. So these are if-then statements. If, for example, we depress the controller button, we push the button, then according to the transition on the left, the response is to start a drive motor pushing the garage door down. One comparison is to think of a state as a room. This room has 2 doors in it. The guy in the room needs to make a decision about which door to choose. In this room, the room itself, we're comparing that to one of these states on the other side. So this state or this room could be that the garage door stopped. The person in the room represents the attention of the computer or the processor. There is also some input data in this room. The input in this case is the laser is blocked. So our task is to inform the processor what decision to make when it has been confronted with this situation. Which door should it choose? Which direction should it go? Should it make the garage door go up, or should it make the garage door go down? So there are many different kinds of state machines. One of the most complicated state machines that I can think of is a vending machine. Lots and lots of states. In fact, this state diagram here doesn't even have enough states to represent this state machine. I think it's more simpler if we consider a vending machine that only vends a single product. That just makes it easier. But examples of state machines that are commonly given are traffic lights, garage door openers, and vending machines. I seem to have a vending machine that has gone missing here. That's okay, we'll continue. How does a person take an idea from their mind and get it into a product, develop it into a useful product like a controller of some kind? Main purpose and value of the state machine diagram is to get the idea from your head to a valuable product. The state graph is a map of their idea. It's sketched out so that the idea comes from your head and gets to be on paper so it can be shown to other people, explained, used to continue making the product. State machine diagrams are also used to populate what we call truth tables. And truth tables are used to convert ideas into equations. Equations guide us in designing the circuit, and then once we have the circuit, we can design the prototype and then design the product from a working prototype. The objective that we're following here is we want to take an idea from our mind. And in our mind, we're going to imagine a machine. This machine, the job we're going to make this machine do, it's a simple job. We're going to design this machine. Its job is to locate a sequence of numbers. So I'm going to stick a sequence of numbers in it, 0, 1, 0. Now, what it's supposed to be able to do is find that sequence in a stream of numbers. As an example of this type of pattern recognition, this might be useful in detecting viruses from streams of data. Probably lots of applications for something like this, but that's just one that comes to mind. One of your handouts, in fact, the main handout for this presentation looks like this. We're going to be focusing on the state graph, or the state machine diagram. And so we're going to only be focusing on these circles. In fact, we're only going to focus on one of the circles to start out with. This circle needs a name. And we're going to use 2 digits in this name. We're going to call this state 0. But we're using 2 digits to represent binary 0 because we're going to need 3 different states. And by using a single digit, we can only represent 2 different states. We're going to call this state start, but that may not be the best name because we might have to return here later. So let's call it start over, which we can do in the beginning or repeat later. Okay. We might imagine that the computer is in this room trying to decide what to do next, or the controller, whatever we do. Let's represent that with a computer. What else? Let's imagine this state has 3 ports. Now, a port is really, you can just think of it like a door, or maybe a one-way door. These ports that we'll be using will have 3 doors. One input door, and then a choice of where to go, out one door or out the other door. And so 3 ports, 1 input, 2 outputs. The door on the left, that's actually a reset that begins the whole process. Imagine that the attention of the computer is directed here. The computer is looking for a specific number or sequence. The number stream is passing within view of the computer or inside the computer. The computer focuses on the first number it sees, and now the computer is trying to decide which door to pass through next. Since this first number does not match the number of the sequence that we're seeking, where should the attention of the computer go? So we're going to choose the top door. If this is the first number in the sequence, well, it's not. This is not the first number of the sequence, so the computer will have to go somewhere and start over. Now, if you're catching this, luckily this door just returns the attention of the computer back to the start over state, because this is not the number we're looking for. Now the computer considers the next number in the stream. Does this number match the first number in the sequence that we're seeking? Yes, it does. Could this value possibly be the first number in the sequence we're seeking? This is interesting. We wouldn't start over. This time the attention of the computer would pass through the other port where this new finding can be considered. This route leads to a different state. We're going to call this state 1. After state 0 comes state 1. But we're also going to give this state a descriptive name. So we have to think about it. What is the meaning of this state? Why would the attention of the computer be here? This is the state where decisions are made when the first number has already been found. So if we're in this state, if we're ever in this state, it means we found the first value in the sequence. All right, so attention of the computer moves to this state because the first 0 in the sequence has been found. So that's why we're here. Next, we compare the next number in the stream. Is this a match? No, the next number we want is a 1 and this is a 0. So where should the attention of the computer go next? Should it go back to start over? Give me a second to think about that. If the next number is a 0, should we go back and start over? Well, actually, even though we found a first 0 and then we found another 0, it might be that this is the beginning of the sequence. So what are we going to do? We're going to return the attention of the computer back to this state, because even though that previous 0 wasn't the first 0, this 0 is or could possibly be the first 0 in the sequence. So rather than starting over again, since we have a 0, we're just going to return the attention to the computer to this state. Another state is needed for when the first 2 numbers have been found. We're going to check the number. Well, we're going to check the next number in the data stream. So there it is. The next number in this data stream happens to be a 1, and we find that that actually matches the number in the sequence. So that's why we need another state. With states named with 2 binary digits, we can actually call the next state state 2, which looks like a 10 in binary, but by now you should know that's a 2. The reason, well, this state acknowledges that the first 2 digits of the sequence have been found, so we're going to name this as well. The first 2 digits, or a 1 and a 0, is found. Now, that 1, 0 doesn't really have anything to do with the name of the state, but it's convenient that a 1, 0, the first 2 digits, have been found. And so the attention of the computer moves to this state, because we found the first 2 digits. Now the computer compares the next number in the stream to the next number in the sequence. Hooray, it's the final number for the sequence that we're seeking. Where should the attention of the computer go next? Should we start over and begin looking for another sequence? Well, no. Starting over is not really the correct direction this time either, because this sequence ends with a 0, which could possibly be the beginning of another sequence. So if we have found a 0, where are we going to go? We're actually going to feed the attention of the computer back to the middle state, state 1, because we have possibly found the first number in a second sequence, and we want this controller to recognize all sequences, even if they are overlapping each other. So the attention of the computer goes back to state 0, 1. And we now acknowledge that we have found the sequence, but now we're on to another sequence, which is why only the first 0 of the sequence in the little thought bubble of the computer is checked. But what if we went back to this state and backed up a little bit, and the number that we found was actually a 1 instead of a 0? Where would we go then? Is that the first 0 of a state? No. If the next number is a 1, we didn't find the sequence, so we wouldn't go back to state 1. If this last number is a 1, we couldn't stay in the same state 1, 0, state 2. We'd have to start over again, right? This is not the right number. So we're going to have to start over, which means we're going back to state 0, 0 to start over, because it just doesn't match the sequence. Okay, and this is, in a way, this is the same as resetting it, in a way. Notice something about this. To find a 3-digit sequence, we were required to use 3 states. Beginning state, a state where the first number is found, a state where the first 2 numbers are found, and then when we find the third number, we don't need a state that says we found the number. We just alert the viewer, the user, the observer, or the computer that we found it, and then go off looking for the next state. Also notice that every state has 2 exits. This means that every possible event has been addressed. Every possible output has been addressed. Moving back. All right, 3 digits, 3 states. Every state has 2 exits. Every possible event has been addressed. This controller can find every sequence in a stream. This is our state graph. It's a representation of the idea that was in our head, but now it's on paper and it can be explained to other people. There is something else we should add, though. Feedback. We want our controller to keep us informed about what it's doing. This machine should give a report to the observer every time it chooses a path. The report should look something like this, A/B. And we will annotate each pathway with the desired report. So we need an A/B report on every pathway. If it chooses that pathway, that is the report that will be given back to the observer, etc. Now, what does A and B mean? A is going to indicate which value was found. A, the input value, determines the pathway. And hopefully you're understanding that now. Another way to say this is that if this is the input that we're looking for, or if this is the input, whether we're looking for that digit, that value as an input, it could be a 1 or a 0. If it's a 1, it should go down one path, and if it's a 0, it should go down another path. So let's think about this for a minute. We were looking for the sequence 0, 1, 0, and the first digit we found was a 1. That's not the first digit we found, so we're not going to go to state 1 where the first digit is found. So if the first digit we came across is a 1, if this is the input, which path would be taken? Hopefully, you're thinking, well, it's the black path above. Yes, and so the report A just tells the viewer, it's just a report of what number was found, and it's explaining why we took this path. So it's a 1. Okay, that works. Now, if you are ahead of me and you understand this, you can actually figure out the value of A before all, or for all of the other transitions before I tell you what they are, but I am about to tell you what they are. The next number we're looking for, well, the next number we found is a 0, and that could possibly be the first number in the sequence. So if it is a 0, then we're going to take the path that leads to the first 0 was found. And so we have to say for our report, A is going to be 0. Now the attention of the computer is in state 1. And we have found 0. We found a 0. We want a 1 to go on to the next state, but we found a 0. But again, this 0 could be the beginning of another sequence. So instead of starting over, we're going to take the black route that leads back to this state, and the number that we were given was a 0, so A will be a 0. Going to the next number. The number, since we are in the state called the first 0 was found, state 1, the next number is a 1, and it just so happens that the sequence needs a 1, and we already found the first 0, and we found a 1, so which pathway should we take, and what is the value of A on that pathway? Well, that is, of course, the only other pathway, and that is that pathway. The report that should be given is a 1. And then we've got the next sequence, but we are now in state 2. That means we have found the sequence of 1, 0. We need another 1 now to find the pattern 1, 0, 1. We have a 0, and that's what we are looking for. So the path we're going to take is the path where, well, we don't start over. It's not the path to start over because it could, even though this 0 is the end of one sequence, it could be the start of another sequence, which means the first 0 is found. So that would be this pathway. And so we're marking that as 0 because that's the number that we got. But if this number was not a 1 or not a 0 and turned out to be a 1, then we'd have to start over. The only other pathway is to start over. And we would give the report, well, we found a 1, so we have to go take the start over path. Okay? So that is how that first part of the report goes. The second part of the report is also feedback, but it's a little simpler to understand. Here we're just saying we chose this path because we got this number, but now it's even easier. This time, the feedback for B, not A. A was the input value, which determined the pathway. But the value of B is the output value, or in other words, should we celebrate because we found the full sequence? 1 is a yes, we found the sequence, and 0 is a no. If you think about it, there is only one place where we have found the full sequence. Do you know where that is? Hopefully you're way ahead of me, and you know that that is the location of when we found the sequence. And so B is the only place that we're going to report that we found the sequence, right? So B is a 1. Now, since that's the only place where we found the full sequence, all of the other B's are going to be zeros, meaning we did not find the sequence. Okay? So anyway, that is our state machine diagram. That's what it looks like. I'm going to turn it into monochrome now because really it doesn't have to have all those colors. This is our state machine diagram. There are some other state machine diagrams I want to show you really quickly. This is one where instead of flipping a switch, you can use a push button switch. You push it, the light comes on. You push it again, the light goes off. Very simple idea. And it's a slightly different kind. This is a, now that I look at it, this is actually not a Mealy state machine. This is a Moore state machine. And we'll be talking about those a little bit later, and you will analyze and have the opportunity to build one of each kind. So this is just another state machine. Instead of putting the reports on the transition graphs, we'll talk about where the reports are later. But this is another one. This is another Moore machine. This is a state machine where a card is validated that it belongs to the user. So kind of another one. This is another state machine that is used to book hotel rooms so that computers can do it, so people don't have to do it. That's kind of the theme of the age of automation that we are currently in the infancy of, and also the age of artificial intelligence, which is just starting at this time. So getting back to this state machine, this is the one we just built, and we're actually going to use this state machine diagram to build an actual simulation. We could actually turn it into a real prototype, and you'll see that. And I don't know, maybe I'll have my students build the prototype. But what we're going to do next, hopefully, looking at your worksheet, you can see, oh, look, there's a truth table, there's some K-maps, and there is a pre-made design. But those 3 squares, those are what we're going to talk about next. Those are the Mealy state machine. So we're going to focus on those next. That'll be the next video. And that's what we'll focus on then. Thank you for watching.